All right, good morning, everyone. Today, we're going to be looking at some basic laws, starting with Ohm's law and some other basic principles related to electrical networks. Last week, we looked at some fundamental principles. We looked at current, voltage, power. We looked at the whole business of power balancing circuits. We looked at the conventions as it relates to current and voltage. So today we're just going to take it a step further and look at some basic laws. Thereafter, we will be able to tackle the more challenging aspects of electrical networks. So let's get started. I start this morning with the thought, all hard work brings a profit, but mere talk leads to poverty. This is a principle that I strongly believe in. As students, we can talk a lot about the things that we think we know, but until we get down to doing it and proving ourselves correct, then we will never be confident in our abilities. So let's take the word of Solomon. All hard work brings a profit, but mere talk leads to poverty. And by that token, I also want you to consider the illusion. Many students have reaped success in electrical networks. The success is what others see. But I do not have to know these students personally. I do not have to be aware of their everyday activities. However, what I can say is that success that they reap comes from them being persistent. Yes, it comes from dedication. It comes from them learning from past failures. Colin Powell, former military officer within the US, once said that there's no secret to success. It is learning from our mistakes. So it's a process of learning from the mistakes. And the question is, you cannot make a mistake unless you try. And so persons who would want to boast that they have never made a mistake is simply because they have never tried. So you're gonna have to try these questions that I give to you. You're gonna have to try problems. You're gonna have to get them wrong. And in getting them wrong, learn from as to why you got them wrong. That success that people see is gonna come from hard work. Many of you are first-year students, but the majority of you are first-year students. You are coming out of high school setting. And I'm fully aware that, things did change when you moved from fifth form to sixth form. So there were certain disciplines that you developed having gone to sixth form. And that can be, that's appreciated. But I'm saying to you know that you are at the university, you still have to make another step up. Yes. And so your approach in sixth form may not necessarily work here in university. If it does work for semester one, fine, then carry on, do what has resulted in your success. But I'm encouraging you that you need to put in some smart work, some hard work, develop some good habits. If you used to play football in sixth form, in high school, continue playing football because it is the physical exercise. It's not just your love for the game, but it was really the physical exercise that made you as sharp as you were in sixth form. So continue playing football, continue having some fun. Not necessarily the type of university fun that many persons are thinking of, but continue having some physical fun. Develop some good habits. Sleep well. There's no rule that says that when you come to the university, you only get 3 hours of sleep. That is rubbish. Many of you are still very young. Some of you are still teenagers. You need 6, 7 hours of sleep. Fine. By the time you get to final year, you be surviving on 4 hours, but get your sleep, get rest, develop some good habits, eat properly. Yes, you need starch, you need energy foods, but you also need foods that will keep you growing and grow healthy. So eat your vegetables and eat lean meats if necessary. There are some things you're going to have to give up. There's no point in trying to fit a party every fortnight into your schedule or every week into your schedule. It's not going to work. Sacrifice that. Give up some of those things that you enjoy. If you're a beach goer, hey, wait until the end of the semester. Right? Manage your disappointments. Manage them. We're all going to be disappointed. And you can only be disappointed if you have certain expectations. So you can't be, you can't be disappointed by persons who you really have no affiliation to. So don't be surprised when you're disappointed, because disappointment only comes from people in whom you had some expectation. So you're going to be disappointed by the people who are close to you. Right? People that you look up to. So manage it. Understand that the people who you have looked up to, they can fail. They have failed, and they may continue to fail. But notwithstanding, you can determine how you address that. So once again, yeah, I know I welcomed you last time, but I welcome you again to Networks. So let us get started. All right, we start with the basic Ohm's law, and the figure on screen represents a graphical representation for Ohm's law. Ohm's law states that within an electric circuit, the current flowing into any part of the circuit is directly proportional to the applied EMF and inverse proportional to the resistance. And that is with the provision that certain conditions remain constant, conditions such as temperature. And I want you to recognize early that in terms of my statement for Ohm's law, I use the current as the reference. So we are saying that I is equal to V, it's direct proportional to the applied EMF, and inverse proportional to R. Now, many persons look at that, they say, yeah, I know this formula, you know, it's nothing fancy. But it represents, for me, the fundamental principle on which we are going to do all our analysis. In other words, from Ohm's law, what I focus on is what's happening to the current. So the current flow will tell us exactly what is happening in the circuit. And you will see that in a few minutes. So graphically, it's a straight line, yes? Passing through the origin, if there's no EMF, if there's no difference in potential, which is the voltage, right? So if there's no difference in potential between 2 points, then you can't have a current flow. Right? So it means that it will definitely pass through the origin. All right? Okay, so there's not much more I need to say on this. So, by example, if we have a voltage, if we have a voltage of 10 volts and a resistance of 2 ohms, of course, I'm introducing the units as we go along here. Yes, then the current would be equal to V over R, which is equal to 5 amperes. Of course, we can rearrange this equation. So we, you know, if we have I and V, we can find R. You know, simple. Some persons use the triangle. Not something that I necessarily focus on. Yes, it says V. Right, the way that most persons would see it. Right? So it's V and I, R. So the one that you're interested in, you cover it. Yes. So if you want V, you cover V, and so V equal IR. Right? But of course, that is when you're in fifth form. we worry about this. You want R, you want V over I. Okay, but at this level, I'm sure you can rearrange the equation for that which you want. So that's the first principle, Ohm's law. I equal V over R. Okay? The law, mathematical representation for the law is I equal V over R. And it is not V equal IR. All right, so this is not the mathematical representation for Ohm's law. All right? That is. Okay? Okay. The next law that we want to mention is Kirchhoff's current law. And Kirchhoff's current law is quite simple. It says that at any node, yes, the sum of the current entering is equal to the sum leaving. So the sum of the currents entering is equal to the sum of the currents leaving. Or in other words, the sum of the currents at a node is equal to 0. So for the figure that we have here, yes, the currents entering would be I1 and I5. And based on the principles that we looked at last week, we know about current direction being pointed out by the arrow. So the currents entering the node would be I1 and I5. So I1 plus I5, that's the sum of the currents entering, would be equal to the sum leaving, which would be I2, I3, and I4. All right? So that's Kirchhoff's current law. Right? Now I know this is a straight video presentation, so normally we would have invited questions, but for now we just work with what is here. So for this figure, all right, if we look at each of the nodes, all right, and by now you would have gone through the exercise, which speaks of nodes, meshes, loops, etc. All right, that's the exercise I gave you last in your first class. So we have these 5 nodes. We have node 1, 2, they're already identified. So we apply Kirchhoff's current law to each of these nodes. Right? And of course, in time you can go back and draw these. But while we are doing that, I'll just do the exercise while you draw this. So for node 1, so for node 1, the currents entering node 1 would be I1. In this case, the current, entering node 1 is I1. Currents leaving are I2 and I3. So I1 would be equal to I2 plus I3. If we look at node 2, so here is node 2. So for node 2, the current that is entering that node would be I4. So we have I4. And the current leaving node 2 would be I6 plus I1. Okay. I'll do one more. So this is node 2. So node 1, this is node 2. All right. We can look at node 3. So for node 3, at node 3, the current entering node 3. All right, so we have this current entering node 3. We have this current entering node 3. So the currents entering node 3 would be I2 and I5. Currents leaving node 3 would be I4 plus I7. Okay, and I leave you to do nodes 4 and 5. Okay. So based on that, based on what we said in terms of Kirchhoff's current law, here we now have a circuit. I have removed the elements, so you know this is referred to as the graph for the circuit. That definition is in your lecture notes. So this being the graph for the circuit, we have here 4 branch currents, and we want to find the currents in the other 4 branches. So we want I1, we want I4, 5, and 6. Okay. So we have to use the branches, or we have to start with the branches that has the most information in terms of the connecting node. So we'll start with node 4. So at node 4, the currents entering that node would be 20 and 30. And the current leaving is I5. So what that tells us is that I5 is equal to 50 milliamperes. Yeah, let me just make sure I write that properly. All right, so it is 50 milliamperes. Okay, so I5 is 50. Now that I've found I5, I can find I4 because I now go to node 3. And at node 3, the current entering the node, yes, will be 50. The current entering is 50. The currents leaving, yes, the currents leaving would be equal to 60 plus, oh, I'm sorry. Why am I? How could I? The currents entering, well, so the currents entering will be 50 and 60. Okay. The current leaving would be equal to I4 and 40. Okay. So 110 would be entering, yes, and leaving would be I4 plus 40, which implies therefore that I4 is equal to 70 milliamperes. Okay. So based on that, I want you now to find I1 and I6. Again, use the information that you have for the various nodes. I think I have done the more difficult one. Okay. Here's another circuit, which I want you now to write the equations for all nodes. So for all 4 nodes, I want the Kirchhoff equations. Okay. All right, I'll do 1. Okay. Let's do node 2. Current entering, I2 plus the current in our dependent current source, which is 50 I2. Okay. And the current leaving, excuse me, the current leaving, so the current entering will be that and that. The current leaving node 2 is I3, which implies therefore that 51 I2 is equal to I3. And that's for node 2. All right. So I leave you to deal with the other nodes. Okay. So in the interest of time, you know, when you're going through this video, you could always pause to draw your circuit. So I'll just move on. Okay. So now we come to the next law. So we have looked at Ohm's. So we have looked at Ohm's law. And we have looked at Kirchhoff's current law. We want to now look at Kirchhoff's voltage law. All right. Now, before I state Kirchhoff's voltage law, what I want us to do is to get an appreciation of two concepts that are very important to circuit analysis. They are known as voltage rise and voltage drop. Okay, a voltage rise and a voltage drop. A voltage drop occurs when there is a reduction in potential when moving from one side to the next of a component. I repeat, the voltage drop occurs when there is a reduction in potential when moving across a component. The reverse is true for a voltage rise. A voltage rise, on the other hand, yes, occurs when there is an increase in potential when moving across a component. So let's say that again. A voltage drop occurs when there's a reduction in potential moving from one side to the next of a component. And a voltage rise occurs when there's an increase in potential when moving from one side to the next of a component. Now, students, based on how we described voltage last week, we know that a voltage is a difference in potential between 2 points. And we looked at how we identify voltages, and we looked at the use of the double notation. We also looked at the use of the plus and minus sign. And we say that the plus is used to represent the point of higher potential. Okay? The point which has a higher potential. And I'll speak to you briefly in a few minutes in terms of how do we put these polarities in terms of the plus and minus on resistors. So we know resistors are passive elements. Notwithstanding, if we look at the circuit before us, we see that the plus represents the point of a higher potential. So if I'm going in this direction, I'm going in that direction, yes, in this case it would be clockwise. Good. If I'm going in that direction in my circuit, then Vs would represent a voltage rise. Yes, we see it as a source, but it's a voltage rise because in going in that direction, when I move from here to here, I'm increasing in potential. So I'm moving from a point of low to higher potential. When I go to this resistor, resistor 1, it would represent a voltage drop because I am entering a positive heading to the negative. So I'm moving from a high to a low potential. And the same thing here, high to low. So these are all voltage drops. So VR1, VR2, and VR3 are all voltage drops. And Vs, in this instance, going in that direction, yes, would represent a voltage rise. All right? Now, having said that, we now look at Kirchhoff's voltage law. And Kirchhoff's voltage law says that within any closed loop, the sum of the EMFs, or in other words, the sum of the voltage rises, yes, is equal to the sum of the voltage drops. So within any closed loop, the sum of the voltage rises, or the sum of the EMFs, is equal to the sum of the voltage drops. So Kirchhoff's law, voltage law, says that the sum of E's is equal to the sum of IRs. That is how we represent it mathematically. But in terms of statements, what we are looking at is the sum of the rises is equal to the sum of the drops. So for this circuit, again, going in that direction, Kirchhoff's voltage law states that Vs would be equal to VR1 plus VR2 plus VR3. Voltage rise, or EMF, is equal to the sum of the voltage drops, as we have just defined voltage drops and voltage rises, yes, or voltage rise. So voltage rise would be given by Vs. Voltage drops would be these three. Okay. Now that's it. Having looked at these three laws, Ohm's, Kirchhoff's current, Kirchhoff's voltage law, we're not going to combine them all and try to expand or open up, our knowledge of circuit analysis. So let's start by first dealing with how it is that I determine which side has a positive sign, which side has a negative. Simply put, for a passive element, so for any passive element, so here's my resistor, and I can draw my resistor as a rectangle, or I can draw it as the squiggly thing that you see there. So whether you want it as that or I don't really don't mind. All right, so for a passive element, the point at which the current enters the component is given a positive polarity. So if in this instance, we're entering from this end, so that's my current, yes, then it means that my positive would be at this end, and my negative at that end. Right? So that's how I put the polarities on my components. And that makes sense because we know that current flows from a high to a low potential. So if the current is flowing in this direction, it means that the potential at this point must be higher than the potential at that point. Okay, so that is how we go about putting on the plus and minus, or the polarities on our passive components. All right. All right, so that's it. Where am I? That's it. For these three resistors, if I had a current I flowing through these resistors, the current would enter resistor R1, and I put on the name, so we have R1 here, we have R2, we have R3. All right. So we have our three resistors. So these are passive elements, and we have already defined what we mean by passive elements. Yes. So the current would pass through resistor R1, and that current would also enter resistor R2. So we can then say that resistors R1 and R2 are connected in series. Now, let's go back to how I define series connections. Two elements, have to be resistors, can be portions of a circuit, which is why I define it this way. So two elements or two components are said to be in series if the current leaving the first is the same current entering the second. Now, I'm not talking just about magnitude. Of course, the same current magnitude can be entering two components, doesn't mean that they're in series. But here, we are saying that they are in series if the same current, in this case I, it's the same current I that is going into resistor 2. And so R1 and R2 are in series. But I also flows into resistor 3. So we can say that resistor 2 is in series with resistor 3. And so that's how we are going to introduce it. So for this circuit, what it is saying to us is that all three resistors are in series. Okay. Now, if they are in series, then it means that we have a series circuit. Now, I know that some persons would have gotten the definition that they are in series because they are connected end to end. Of course, we connect things end to end. Doesn't necessarily mean that they are in series. But that's for another discussion and for another time. Here, we have a series circuit. Okay, so I have a series circuit. And in this series circuit, we're going to apply Kirchhoff's voltage law, which we have already written. So in this instance, Vs is equal to VR1 plus VR2 plus VR3. All right. However, based on Ohm's law, we know that I is equal to V over R, which implies that V is equal to I times R. Yes. So substituting into our equation, it means that Vs is going to be equal to I times R1 plus I times R2 plus I times R3. All right. Which implies, therefore, that Vs, and since the same current will be passing through each, yes, would be I into R1 plus R2 plus R3. Okay, or Vs over I. So that the supply voltage divided by the current, which would be the circuit current, would of course give you the total resistance, yes, which would be R1 plus R2 plus R3. So the total resistance for elements in series, for your series circuit, would be R1 plus R2 plus R3. Okay. All right. Now, this also leads us to determine, let's say we wanted VR1, right? Or VR2. Let's use VR2. We know that VR2 is equal to I times R2. But based on what we just saw, we know that I is equal to Vs over RT, which implies, therefore, that VR2 is equal to Vs times R2 over RT. Okay? So in other words, if we have for series connected elements, right? So for series connected elements, if we want the resistance across resistor N, so for N elements connected in series, VRN would be equal to Vs times Rn over RT. And this is known as the voltage divider rule. That's the voltage divider rule. So for N elements connected in series, the voltage across any is given by Vs times Rn, that's the resistor you're interested in, over RT. Okay? So two things we have. We have the voltage divider rule, and we know that RT for your series connected resistors, RT is equal to R1 plus R2 plus R3 plus up to Rn. All right, so let's go back to the principles outlined in Kirchhoff's voltage law. Yes? And remember, we were saying we want to look at, or just helping us to understand the whole principle behind voltage rise and voltage drop. So let's start at point F. Yes. So I'm going, well, you know, why start at point F? Let me start at point A and just do let's go according to the alphabet. So if we start at A, VR1, so I'm going to write down the voltage drops that I encounter. And then we're going to write down the voltage rises that we encounter. So starting at A, VR1 would represent a voltage drop. So that would be first one in our drop category. Then we go to B. Between B and C, I'd experience a voltage rise. So that would be 5. I then go from C to D. I have a voltage drop. So VR2 is a voltage drop. From D to E, I have a rise, so another in the rise category. And then from E to F, I have another voltage drop, so that would be VR3. And then from F to A, we have a voltage rise, which would be 30. So according to Kirchhoff's voltage law, 5 plus 15 plus 30, which is of course equal to 50. So 50 is equal to VR1 plus VR2 plus VR3. Okay. Let's extend that a bit. Let's see if we can now use that to, do some calculations. I want to verify Kirchhoff's voltage law. So let us see if that is the case. So I'm going to give it the voltages. Yes. So the question here is to verify KVL. All right. Starting at A. Starting at A. Remember now, we're not looking at the type of element. What we're looking at is whether we have a voltage drop or a voltage rise. So for the drops and for the rise, starting at A. From A to B, I have a drop of 24. From B to C, I have a drop of, a rise rather, of 4. From C to D, I have a drop of 6. From D to E, I have a rise of 12. From E to F, I have a rise of 8. And from F to A, I have a rise of 6. Okay, so what we have therefore is 4 plus 12 plus 8 plus 6, right? Which gives us 30. And on the drop side, we have 24 plus 6 to give us 30. All right, now remember, what we just did was to look at the current or look at the circuit going in that direction. However, if you had done that and go in that direction, you have the same result, just that the rise would become, but that's the same direction I'm going in. Well, today is not my day, is it? All right. So if we went in that direction, yes, if we went in that direction, then we'll have the same result. Just that the rise, so the voltage rise would now be 6 and 24. And the drops would be the 4, 6, the 12, and the 8. So again, 30 would be equal to 30. Nothing would have changed. Okay. All right. All right, so next. What I want us to do is to write the loop equations. Okay. So we have this loop, we have this loop, and of course we have this loop. Right? So we have 3 loops. Of course, 2 meshes, 3 loops. So just to start us off, I will do the first loop. But I'll do one of the loops. Now, one of the things that must be done when we're writing loops is that we must label the loops, and the loops must all close. All right? What do I mean by that? If we're labeling loops, then let's say we're doing the outer loop. Then it would be loop A, B, C, D, F, and back to A. All right, so it will be this loop. So there's no question about the loop that we're doing. All right, so for that loop, that's the equation we're going to write in. Okay. All right, so for that loop, voltage rise. So now that I think we have the understanding, yes, and we're going in that direction. So we'll have 24, yes. Now, if we want to look at sources, you know that we have the 24, but here, because we are now going into the positive of the 8, it now goes on the side of the voltage drop. So I would say 24 minus 8. If we want to look at sources, okay? Here we have plus, plus, plus at the start of each resistor. So 24 minus 8 would be equal to VR1, VR2, and VR3. Okay. So I leave you to do the other two loops. Okay. So VR1, 2, and 3 would be equal to 16 volts. Now for this exercise, we want to find VBD. So we want to find the voltage here. Right. The first thing we need to do is to determine what VR1 is equal to. So to determine VR1, we're gonna have to determine, yes, or write KVL. So the voltage law for this circuit, remember, within a closed loop, sum of the EMFs equal to the sum of the voltage drops. So here, I'm going to write the expression for the voltage rises. So in this instance, it will be 12. So we have 12 is equal to, in terms of voltage drops, we have VR1, we have VR2, and of course we have the 10 VR. So we have VR1 plus VR2 plus 10 VR1. All right. So we have VR2, which is 1, plus 11 VR1. Okay. Which implies that VR1 is equal to 1 volt. So now I can start determining what BD is equal to, and I can go from whichever direction I choose. So let's start at D. All right. So if I move from D to A, all right, I would have a voltage rise of 12 volts. Okay. And then when I move from A to B, I would have a voltage drop of VR1, but we know that VR1 is equal to 1. So VR1, I'd have a voltage drop of 1, which is equal to 11 volts. So it means, therefore, that the rising potential from D to B, going in this direction, an increase in potential from D to B, yes, would be equal to 11 volts. Because I rise 12, drop 1. But if I start at B, all right, knowing that we have 11 volts there, yes, I go from there, so I'd have 11, and I have a drop of 1, yes, and a further drop of 10, because that's 10 VR1. which gives me 0, which means that I am back at D. So I have dropped by 11 to come here. So the difference in potential between these 2 points is 11 volts. Okay. All right. So I introduced you earlier to series connection. All right. We're now going to introduce you to parallel connections. Okay, or parallel connected resistors. So for my parallel connected resistors, here we go. Now, my definition. Firstly, we want to consider Kirchhoff's current law. In this instance, a current entering the node, and we agree that all of this is a single node, right? So all of what we have there is a single node, because of course there are no resistors in between, so there's no voltage drop, so it's a single node. I could have drawn it like this. That's a node, and then I have one resistor there, one here, and one here. If I had done that, then I think persons would be better able to agree that this is a node connected to my supply. Right, so I've not changed anything, just that I've stretched out that node as a line. Okay, and again, we go back to what we described as a lump parameter circuit and what having the lines represent. Okay, so all of that we have discussed already, all of that is tied in right now. Okay, so we have our node. Kirchhoff's current law says that the current entering the node is equal to the sum of the currents leaving. So it means that I1 is equal to that I is equal to I1 plus I2 plus I3. All right, that is what we get from our circuit. So the current entering, which is I, is equal to the sum of the currents leaving, 1, 2, and 3. Okay, but again, Kirchhoff tells us that the current I is equal to V over R. All right. Now, folks, let's go back to what we said earlier. If this is a node, and then this is also a node, what we can say is that the potential between this node, yes, and this node, the potential difference between them would be equal to E. So the difference in potential between those two nodes is equal to E. Therefore, the potential across each of these resistors would be E, because these resistors are connected between those two nodes. All right, and so V here would be equal to E. So I1 would be equal to E over R1. I2 would be equal to E over R2. And I3 would be equal to E over R3. And before deriving the statement, I want to talk about parallel connected elements. Right? Note parallel connected elements. What do we mean by that? Simply put, two elements are considered to be in parallel, or elements are connected to be in parallel, if the current entering the node connecting the two elements divides between them. Now that's for two elements. In this case, we have three. So we just expand that definition to say that the three elements are in parallel because the current entering the node connecting them. This is the node connecting them. And this current divides based on that. So in this instance, let's go back now. I is equal to I1, 2, 3. So it means that I is equal to E over R1, E over R2, E over R3. All right. Or I is equal to E into 1 over R1, R2, or I over E is equal to 1 over the total resistance is equal to 1 over R1, 2, okay. Hence, RT for your parallel connected resistance is equal to R1, 2, 3. Right. So for N resistors connected in parallel, yes, it's 1 over R1 plus 1 over R2 plus 1 over R3 plus up to 1 over Rn to the minus 1. Okay. All right. So, quick example. We have 3 resistors, and the question is for us to, for a supply, the question is for a supply of 20 volts. So it means that E is 20 volts. Calculate the current supplied by E. For a supply of 20 volts, calculate the current supplied by E. I want the power dissipated by each resistor. So that's part B. So the first is to find the current supplied by the source, 20 volt source, and to find the power dissipated by each resistor. Okay. All right. So we're going to use 2 approaches. First one is to find the total resistance. So RT would be equal to 1 over 30 plus 1 over 10 plus 1 over 15. All right, and we're going to find the reciprocal of that. Okay, so we have here 30. We have 1 plus 3 plus 2. All right. That gives us 6 over 30. All right. That RT is equal to 5 ohms. Okay. So the current from this, from the source, so I would be equal to 20 20 divided by 5, which is equal to 4 amperes. All right. We can, however, also use the current through each resistor and then add them, because we know that from Kirchhoff's current law, the sum of I entering, yes, is equal to the sum of I leaving. Okay. So for the 30 ohm, we'd have 20 over 30. So that's 2 over 3. For the 10 ohm, we'd have 20 over 10, which gives us 2, of course, amperes. And for the 15, we'd have 20 over 15, which gives us 1 1/3. Okay. So IT will be equal to 2/3 plus 2 plus 4 over 3, which gives us 4 amperes. So we come back to the same result. Part B asks us to find the power dissipated by each resistor. So for part B, let's use a different color ink for that one. We know that the same voltage is across each. So for the 30 ohm, we're using P is equal to V squared over R, or we can use P equal to I squared R. All right, let's use I squared R. So for 30 ohm, it would be 4 over 9, that's I squared, times 30. For the 10 ohm, it would be I squared R, so that's 4 times 10. Okay, and for the 15 ohm, it would be 16 over 9 times 15. Okay, I think I can erase the cell at the bottom here. So give me some space. Okay, of course you can plug this into your calculator and you're fine. You don't have to go through this long road. But hey, I'm a sucker for punishment. So for the 30, we have that will be 40 over 3. Here we have 40. Yes. And here we'll have 3 into this. That's 3. 5 times 16, that's 80 over 3. Okay, which gives us a total of 240 over 3, which gives us 80 watts. So this is the total. Of course, you know, these are the individual powers. So this is for the 30 ohm, this is for the 10 ohm, and that's for the. But I went ahead and found the total because this will tell us whether or not we are correct. So we know that the total is 80 watts. For our source, we had 20 volts, and we know that the current being supplied is 4 amperes. So this gives us 80 watts, which is what we should rely on, students, in terms of our power balance to know whether or not our calculations are indeed correct. So the power balance here, sum of the powers for the resistors is equal to, and we know that it's being absorbed. Why? Because we know that current is entering the positive. Because remember, these would have had positives at the top here. Yes? Because we have spoken about how to put the polarities onto our passive elements. And the current is entering these positives. So therefore, these are absorbing power. And of course, it is being supplied by E because the current is leaving the positive. All right. Finally, this morning, finally today, we have two resistors in parallel. They are in parallel, not based on how they are drawn, but based on what we said earlier in terms of the current entering the node which connects them. So RT would be equal to 1 over R1 plus 1 over R2, the reciprocal of that, which in this case, we'd have R1, R2, R1 plus R2, the inverse of that, which would be R1, R2 over R1 plus R2. Okay. Now, if I wanted the current in resistor 2, so I want IR2, yes? So to find IR2, IR2, is equal to E over R2. But E is equal to IT, which is the total current, I, yes, times R2. So it will be I times RT over R2. Right? Where, of course, this is E. And so let's erase what's at the bottom here. Okay. So it implies, therefore, that IR2 is equal to IT, which is the current entering out. Let's call it IT. It's not denoted as IT there. Times RT over R2, which would therefore be equal to IT times R1, R2 product over sum R1 plus R2, yes, multiplied by 1 over R2. Okay, so the R2's cancel, and I'm left with IT R1 over R1 plus R2. Okay, now and this is equal to IR2. If we therefore needed IR1, it would be IT R2 over R1 plus R2. No, we can do this one many resistors in parallel. However, it is of no benefit for us to do that. None. And we just keep it simple. So we'll only do it for two resistors or resistances. And I'll explain that at another time. So IT times R2 over R1 plus R2 gives us IR1. And for IR2, it's IT R1 over R1 plus R2. In other words, this is known as the current divider rule. So we looked at the voltage divider rule earlier. This is now the current divider rule, and it states that the current, if you want the current for a particular branch, then it is the total current entering that node times the other resistance over the sum. So if you want current through R1, you're multiplying by R2. If you want the current R2, you're multiplying by R1. All right, and that is it for today. This has given you all the fundamentals, okay? And your independent study will be a lot easier going forward. So thank you very much for your attention.